My name is Teresa Wriston. I'm a geoarchaeologist at the Desert Research Institute.
My name is Christina Neudorf. I'm a geochronologist at the Desert Research Institute.
So the Great Basin during the late Pleistocene was a land of lakes. And the southern Great Basin, even north of Las Vegas, had the same kinds of lakes, big, expansive lakes that filled most basins. And here in Coal Valley, there was a big lake around 16,000 years ago that would have been lapping the shore right here. So we've been trying to get age control on the high stands of these pluvial lakes throughout the Great Basin. And we're running into a number of obstacles. Because of their location, their topographic location tends to be highs. They're usually eroded except for the gravel cap. And a lot of times charcoal doesn't preserve, or there were no trees or good chunks of charcoal originally. And also shell can be contaminated by old carbon. So we've really been struggling to try to get some of these old high stands dated. And luminescence really offers us the opportunity to date the class specifically. Unfortunately, we've been running into problems with the fine grain luminescence because sand will work its way through the pore space of those old beach gravels. So it's given us ages that are too young. But this method that Christina is developing at DRI uses the actual beach gravels themselves, the rocks that were moved by wave action by the ancient lake. So that's a much more direct date of those ancient shorelines.
Luminescence dating is about determining the last time sand grains or rock were exposed to sunlight. So what that means is when we're extracting the sample, we cannot expose that sample to sunlight again. Otherwise, we're resetting the clock and we're going to ruin the sample. It will be useless. So we need to take the samples in such a way that we do not actually expose them to sunlight again since the last time they were deposited. And we can do this a number of ways. When we're sampling sand, we can take a PVC tube or pipe and we can hammer it into the section and extract that so that the sand inside has never been exposed. But when it comes to more complicated samples like rocks, sometimes we have to go out in the middle of the night and perhaps set up a tarp to block any moonlight and clean the face or dig a new pit and then extract samples that way.
And we use the red, very low light conditions, so we can see with the red light, but it won't reset that clock.
Yeah, so red light or very dim red light of a very specific wavelength does not actually reset that clock. We know that from experimentation. So we can operate at night using red headlamps or flashlights so we can actually see what we're doing.
Unfortunately, this process is not always easy, and that's usually because of preservation. And preservation of the landform, like for instance, there were probably shorelines in the interior that had been wiped out because they weren't capped by gravel. Preservation is always an issue. Exposure, natural exposures by rivers is really important for us to discover things, right? If they're not on the surface, we either have to dig for them or infer and then try to dig for them. So obscurity is a problem, but probably one of the biggest challenges are these locations tend to be remote and usually weather can fight you, you know, big temperature swings, and we're
wind.
Yeah, wind is a big one. Mm-hmm. And we can be setting up a dark tent and digging with dust and heat inside. So there's a lot of challenges associated with this type of science.
Night sampling as well. So we have to sample right up until midnight or 1 o'clock, depending on how successful sampling is.
Yeah, and lack of sleep.
Yeah.
So trying to sleep in a tent just doesn't work when it's 100 degrees outside.
Yeah.
So there's lots of challenges, but we definitely think those challenges are worth it. I mean, we're getting some great data.